So it's just you and I here, Sebastian, for now. So thanks for coming. Just a reminder that we have the exam coming up on Thursday. It'll be 10 multiple choice questions and 2 long answer problems. And it'll be gated in the way that we talked about last class. The other thing, which we were just talking about, right? So I guess it's just you and I again, but for the benefit of people watching virtually, I suppose, this is the homework that's on the syllabus for this week, right? So there's, I don't know how many questions this is, 6, right? But only 2 of these problems are related to the stuff that's on the exam. So for this week's homework, I'm going to ask you to do those 2 problems and then study for the midterm. And the stuff that's on open systems we'll make do at the end of next week. So in next week's homework set. So if you already started them or whatever, like don't crinkle it up and throw it away, right? You'll still need to submit it again the week after. But this way, I want you to be able to put your focus towards, the stuff that you're going to need for the midterm, which is coming up next week. Did you have other questions about any of the homework or anything?
No, this is fine.
Okay, thanks. Michael, thanks for coming. I just wanted to, I'll send an email after the class, but I just wanted to let you know that for the homework, I'm going to push the open system stuff, the problems in chapter 4, to being due not in this next homework set, but in the homework set after that, just because it's not really related to the exam, and this way you'll be able to focus more on what you actually need for the exam. Okay, so we have been talking about conservation of mass, right? Because we know that ultimately what we want to be able to do is look at these open systems where mass can pass in and out of our system, and we want to figure out what's going on with the energy. But one of the things we've learned so far in this kind of first third of the class is that mass carries energy with it, right? So if mass is coming in and out of the system, then it needs to, or then it's going to bring energy with it, right? So we've been talking about open systems now for a couple of days, and we've got this idea of conservation of mass, right? So that means that whatever you had at the beginning is what you have at the end, but maybe something came in and out of the system, right? So, for the exam, we talked about the closed system stuff, right? Delta E is equal to Q minus W. You find work is the integral of PDV, and then you need to know what's in the system in order to find the specific internal energies. Right? And now we're on the path to figuring out what happens when we have a system that's open, when mass can come in and out of the system. Right? And we talked about how this is actually how an internal combustion engine works, right? That it's taking air in from the environment, and there's fuel that's being pumped into the system, and then you have exhaust that's coming out. So there is mass that's coming in and out in different shapes and sizes. Right? So when we have these open systems, the first thing we need to do is we have to define where our system is. We have to draw our control volume. Then we have to ask what happens to the mass, and that's kind of what we're learning about now. And then after that, the next thing that we'll start to learn about, maybe next week, is what happens to the energy in these open systems. Right, so I drew this kind of sketch, right? And I said that, well, what we know, if we look at elapsed time, which we don't often do with open systems, but if we did, then we know that if I want to know the difference in mass between the beginning and the end of my problem or my process, I just have to count all the mass that comes in over time and all the mass that goes out over time, right? That the change in mass is equal to the sum of the mass that comes in minus the sum of the mass that goes out. Now, we also had this special case, right? This thing called steady state. So at steady state, none of the quantities, nothing that's going on inside the system changes with time, right? And since the amount of mass in the system is some quantity that's inside the system, it also doesn't change with time, right? So right now, this water bottle is at steady state. It's closed. Well, 1 second here. Now it's an open system, right? But nothing exciting is happening because the mass is just staying constant, right? Now we talked about we could get some state where it's raining outside, so there's water coming in the top here, and then there's a leak at the bottom. And even though stuff's coming in and stuff's going out, if it's happening all in balance, then the amount of mass inside the system can stay the same, even if it's not the same water molecules in there. Right? Now, normally when we're talking about open systems, we won't be looking at changes over time, right? That's typically how we deal with closed systems. We look at elapsed time type problems. But with open systems, we're typically interested in what happens in a particular instant in time or at a particular snapshot, right? So then we have to take that elapsed time version of conservation of mass or continuity, and we take the rate version of that equation, right? So we talked last class, you divide by delta t, you take the limit as delta t goes to 0, and you get this expression, right? That the rate of change of mass in the system is equal to the sum of all the mass flow rates coming in minus the sum of all the mass flow rates going out. And again, we can have this steady state case. This happens only when the amount of mass in the system is not changing with time. So the rate of change of mass in the system is 0, right? Which means that the mass flow rates in have to be the same as the sum of the mass flow rates out, right? So that's that case, right? Where the water bottle's here and it's raining and it's leaking, but the water level stays the same, right? It's kind of this magical case, right? Where it looks like nothing is happening if you're only looking at the mass flow rate, but it's really just that nothing is changing, that we're at steady state, or sometimes people would say equilibrium, right? Equilibrium because things are being equal, held equal, they're not changing. Right? So the cool thing about steady state is that at steady state, the sum of all the mass flow rates that go in is equal to the sum of all the mass flow rates that go out, right? That's what this conservation of mass is telling us, right? That if dm by dt is equal to 0, then all the mass flow rates in have to equal all the mass flow rates out, because otherwise you would be gaining or losing mass. So we're going to do a couple of different examples, right? And the first one I'm going to go through pretty quickly. It's a little bit silly, maybe, probably because my kids are too young. I watch a lot of Disney movies, right? And this was Disney's take in Jack and the Beanstalk, right? So you know, Mickey and Goofy and Donald over here, they don't really have anything, right? They're pretty sad. They live in this desolate wasteland. And Mickey takes the cow, right? The cow is like the only thing they own in the world, and he's supposed to take it to market to get some money so they can get some food. But instead he trades it for some magic beans, right? And Donald is like super upset, right? So he takes the beans and he just chucks them out the window, right? And Mickey's like heartbroken. He feels bad. He feels like he let his friends down, right? So this part's not in the movie, right? But, you know, Mickey feels bad because he feels like he let his friends down, right? So he's like, well, if all we got are these beans, I'm going to make the best of it, right? So they've got a reservoir full of water. Doesn't rain much in their desolate wasteland, but, you know, they've got some water that they've stored up. There's 10 liters, right? Now, on the first day, on Monday, Mickey takes 2.5 liters and he waters the beanstalk, right? And then Goofy's on board. Goofy's a nice guy. He just wants his friend Mickey to be happy. He gets another 2.5 liters and he waters the beans the next day, right? Donald's less excited about this project. So he waters the beans, but it's kind of half-hearted, right? Half a liter. Right? But then Mickey, I don't know, goes down to a stream or something and he adds 3 liters to the reservoir and then he waters the beans with 2 liters, right? And then Goofy's, you know, he's kind of getting less excited, right? So 1.5 liters he waters on Friday. So now the question is, how much water is left in the reservoir, right? Now, there's one thing that you might notice here, right? We've been talking about conservation of mass, right? Now, these are metric units, right, which you may or may not be familiar with, but in a metric system, mass is measured in grams or kilograms, right? Volume is measured in liters. Now, there is no such thing as conservation of volume. Conservation of volume does not exist. So in order to answer this problem, we really need to know the density of water, right? But the first thing we would do here is we would say, oh, liquid water. Remember from before when we were talking about liquid water, we said, oh, it's actually incompressible, right? Or very close to being incompressible, that the density of water doesn't change very much, right? So here we're going to assume that the density of the water here is constant. So then if we wanted the mass of water that was coming in and going out, we would multiply the density by the volume, or the volume changes, right? Because the density is constant, it can just drop out of our equation because it's on both sides, right? So how much water is left, right? I mean, I could probably ask my 11-year-old could certainly do this, right? It's just some subtraction and stuff, right? But she probably wouldn't say, well, I got to assume that the density of the water is constant, right? And about 1,000 kilograms per meter cubed. But she could come through and do the subtraction, right? Maybe another assumption that we have here is that they're covering up the reservoir so that, all the inflows and all the outflows that we have listed here are the only inflows and outflows that they are. But if we do that, right, we can look at this and we say, oh, that the mass at the end minus the mass at the beginning is equal to all the mass that comes in minus all the mass that goes out, right? So we're told how much volume is there at the beginning, right? And we're trying to find how much volume is there at the end, right? So, I don't know if you watch this movie, right? Because it's a classic Disney movie, right? Like they really do something kind of terrible, right? Especially in the old school version here. They climb up this thing, they steal the giant stuff, and then they kill the giant, because he's climbing down and they chop down the beanstalk and he dies, right? Because that's how old fairy tales are always like super brutal, right? The new version though, that's on like Disney Plus here, it's like, the giant comes down and they all become friends, right? Because, it's the magic of friendship, right? But here, so we can add this up. I don't even think I did add it up here, but we know that we started with 10, right? Minus 2.5, minus another 2.5, then we're at 5, then at 4.5. Mickey adds this up, that's 7.5, but, down to 5.5 again, down to 4, down to 4, right? So I think we get 4 kilograms per meter cubed if I did all that math right in my head. But anyway, you can see that it's just a series of subtractions, right? It's pretty straightforward, hopefully, even though maybe I just screwed it up live. I don't know, right? So we can get a number here, right? We don't typically talk about conservation of mass from this elapsed time version because it tends to be relatively straightforward. Although you can get a case where you're not given discrete amounts of mass that's coming in and out. Maybe you're given some sort of mass flow out that's changing over time. And then you might have to like integrate it over time or something. So you could end up doing that. There might be one homework problem that's a problem like that, but that's typically not something we do in this class, right? When we're talking about conservation of mass, right, and conservation of energy, we're typically interested in a situation like this. So this is a turbine. Do you guys know what a turbine is? It's sort of like, it's okay if you don't, it's kind of like a windmill, right? So a windmill has fan blades, right? And what happens is as the wind blows over those fan blades, right, then the fluid pushes those blades and makes it spin, right? And then because it's spinning, what happens is we're mechanical engineers and we say, oh, there's some mechanical energy there, right? So, way back in the day, maybe there's, people had like a sawmill and they had like a paddle wheel in a river, right? And then that would make the wheel spin and you could hook that up to some kind of machine that was like cutting wood for you, right? But now we have friends who are electrical engineers, right? And they see a spinning shaft, like what happens in this turbine, right? And they say, oh, I could hook that up to an electrical generator and we could put, energy out on the grid, right? So this is what we're doing here. Inside this turbine, though it's not shown here, is basically just some very well-designed fan blades. And what happens is we boiled some water, right? So now we have steam, and that steam wants to expand. So it's trying to expand. It's going quickly over a bunch of fan blades, right? And that's causing this shaft to turn. And then what happens is some stuff comes out over here that's not this sort of high pressure, high temperature steam, right? This is kind of like, you could take like the computer fan that's in your computer and like blow on it, right? And it would spin. right? That's kind of what a turbine does, right? So it's changing this energy that's wrapped up in this high pressure, high temperature steam and turning it into mechanical energy, right? We'll talk a lot about turbines as we move on, as we start to worry about the building blocks of things like, nuclear power plants or jet engines, right? So turbines become pretty important. But I think this may be the first time that we've talked about them in class. But for right now, we're trying to do a mass conservation problem, right? So we're not worried about the energy here. We're not worried about the spinning shaft. What we know is that we have a turbine. And the turbine, by the looks of it, has one inlet and two outlets. Now, in this problem, we're also told that the turbine is at steady state, right? Which means that nothing is changing over time. So there's a pressure, a temperature, and a volumetric flow rate at this inlet, and they're always going to be the same, right? And this mass flow rate out, right, and the temperature and the diameter here, that's also all going to be the same, right? Same as over here, right? So we're taking this snapshot and we're trying to figure out what's going on with the mass here. Now, in particular, what the problem asks us is what's the velocity at the exits? So there's two exits of this turbine, right? So what's the velocity at these two exit ports, right? So now we'll try to answer this problem, right? So here we have the same problem, right? And we're asked to find, we want to find the velocity at 2 and the velocity at 3. I guess it's really maybe just the speed because we don't care about the direction. Here's the information that we're given, right? And because we know that this is a conservation of mass problem, and it's also a rate problem, right? We've got two different kinds of equations, right? So we've got this, which is our governing equation. This is the conservation of mass or continuity, the rate version that we will typically use for open systems. And then we know that we're going to typically define m dot, or if we need to find m dot, it's going to be the area times the velocity, right? Or this part on top. This could also be called the volumetric flow rate, right? Because area, which is in meters squared, times velocity, which is in meters per second, could also be meters cubed per second, right? So this is what's the volume of fluid that's coming through at a particular time, right? So now we want to make some assumptions, right? Now the problem has made at least one. So I guess the first thing is it's an open system, right? Because it's an open system, then that means we can use this equation here. The next thing that we want to know is that, right, so our equation looks like this, dm by dt is equal to the sum of mass flow rates in minus the sum of the mass flow rates out. But we're also told that we can assume that this is at steady state, right? So that means things aren't changing over time. Right? Now remember, the reason that we write some of these things with a dot over them and some as d something by dt is because this represents something that's stored or depleted in the system. Right? So this is the rate at which mass is changing in the system. Right? But at steady state, nothing is changing with time. Right? And since mass is something in the system, then we know that the mass stored in the system is also not changing because we're at steady state. So now we know that 0 is equal to the sum of the mass flow rates in minus the sum of the mass flow rates out. Right? Or we know, so we look here, right? There's one inlet at state 1. Right? And there's two outlets at state 2 and state 3. So here I could rewrite this as m dot 1 minus m dot 2 minus m dot 3. Oops, this should be an equal sign here. So what I could do, right? Let's say I like positive numbers, right? I want to put the mass flow rate at state 1 is equal to the mass flow rate at state 2 plus the mass flow rate at state 3. So, I'm at a point right now where I've got an equation that hopefully will be able to give me some of what I want, right? But now maybe I want to go back and see, maybe I call this equation 1, right? I want to go back and see what is the problem actually asking me for, right? It's asking me for velocities. But if I look here, there's no velocity in my equation. That means I can't use this equation to find the answer that I want, right? So now I got to rack my brain a little bit. So I need to remember, and I guess I wrote it up at the top of the thing already. So remember, how do I start with, how do I get the mass flow rate as a function of the fluid velocity, right? So what we know is that we talked about mass flow rate being equal to the area times the velocity divided by the specific volume. So I'm going to take this and I'm going to put it into equation 1. But I'm going to do that 3 times because I have 3 different mass flow rates here. Right? So this is going to become the area at 1 times the velocity at 1 divided by the specific volume at 1 is going to be equal to the area at 2 times the velocity at 2 divided by the specific volume at 2 plus the area at 3 times the velocity at 3 divided by the specific volume at 3. This equation's nice because the things that I would like to find are V2 and V3. So both of the things that I would like to try to find are in this particular equation, right? So that's pretty good. So I can start to look at this guy, which is now my, I guess, equation 2. And I can start to think about the things that I know and the things that I don't know. Now, the bad news for this problem is I don't know the area at 1. I don't know the velocity at 1. I don't know the specific volume at 1. I don't know the area at 2 or the specific. So I actually don't know anything, right? I've got 9 things in this equation and I don't know any of them, right? But at least I got an equation. I got something, right? I have a symbolic, kind of a symbolic solution for what I'm trying to look for, right? So let's go through the inventory and see what it actually tells us, right? So here it's told us a bunch of state information, right? So in my expression, right, I'm trying to find V1, V2, and V3. So this stuff is going to be important. So, but if I can fix all my states, then I could get to those velocities. It's also told me that the volumetric flow rate, the area times the velocity at state 1, is 236 meters cubed per minute. So that means that even though I don't know the area or the velocity at 1, I do know what the product of these two things is, right? So this is good. I know that. Hopefully, for these 3 guys, I can fix the states. And then for these 2, what it tells me at state 2 and state 3 up here, it gives me the diameters. So because it gives me a diameter, I'm going to assume that these are circular in cross-section, right? So D2 is 0.25 and D3 is 1.5. So I have D2, 0.25 meters, and D3, what did I say, 1.5 meters, something like that, right? So here I can also remember that area is equal to, I always prefer to say pi r squared, but you could also do pi d squared over 4. The reason I don't like this one is it just gives me a chance to mess up if I don't have this memorized, because you know, the radius is d over 2, right? So, but I got to remember to square that 2 on the bottom, so this becomes pi over 4, right? But here, so I could get a1 from here, right? I can get a2 and a3 because I know d2 and d3, right? So here, well, I think I'll just pull it up because I will have the solution over here. So because I know the diameters, I can figure out the areas, right? So here, oops. I get 0.25 times 0.25 times 3.14 divided by 4. I get 0.05, so this is 0.05 meters squared. So that's the cross-sectional area for this smaller pipe. And the cross-sectional area for the larger pipe is 1.77 meters squared. Right, so now, in my expression, these things are known. And I can fix these states, right? Which I'm going to do, but I'm going to wait a second because I notice now, right, that even if I fixed these states, I'm still in a bit of trouble here, right? Because let's say I fix these states. Let's say this is 1 and half and 1 1/2, right? So it's just some numbers. I know these things. I know the areas now. I know AV, but I just got one equation and I have 2 unknowns. So there's something else that I need in this problem, right? So we can go back up here and we notice that it tells me that 20% of the mass, 20% of the mass flow rate that comes in here at state 1 comes out at state 2. So what does that mean, right? I can look, before I wrote down this version of the equation, I wrote down this version of conservation of mass, right? Because we're at steady state, the mass flow rate of 1 is equal to the mass flow rate of 2 plus the mass flow rate of 3. But it tells me that the mass flow rate of 2 is equal to 0.2 m dot 1. Right? So here, I mean, maybe you just do this in your head, right? If I tell you that all the mass flow rate in is equal to all mass flow rate out, and 20% of it comes out at state 2, maybe you know this, but I can do the math, right? And I can rearrange this, and I'd say that m dot 1 minus 0.2 m dot 1 is equal to m dot 3. So m dot 3 must be 0.8 m dot 1. Right, so from here, I actually get 2 separate equations. I get that m dot 2 is equal to 0.2 m dot 1, and that m dot 3 is equal to 0.8 m dot 1. So even though this expression is true, and if I could, so I guess I got 2 paths that I could take here, right? And neither is wrong. Right? I could use, say, this version, this expression, and get V2, and then use this expression to get V3, but I think that's too much substitution, right? So I think what I'm going to do is I'm going to take this equation and write those out using the idea that, right, so here I had m dot 2 is equal to 0.2 m dot 1. Right? But we know that m dot 2 is a2 times the velocity at 2 over the specific volume at 2. And that's going to be equal to 0.2 times A1 V1 over specific volume at 1, right? I can rearrange this. Oh. Sometimes, I don't know what happens with the pen. I wonder if there's 2 buttons on the top of the pen and one of them is erased, right? So here we know that, what did we say? We said A2 V2 over little v2 is equal to 0.2 A1 V1, right? This is just one term divided by little v2, right? Or because what I actually want to get is an expression for v2. So this velocity at state 2 is, I don't know, the gremlins are out here. My velocity at state 2 is going to be, okay, I'm going to use PowerPoint because for some reason my thing is not working. So here, my velocity at state 2, I can find here, right, by manipulating this equation, right? So my velocity at state 2 is equal to m dot 2 times v2 over a2, right? But we know we could have written m dot 2 as we know that m dot 2 is equal to 0.2 m dot 1, right? So I could rewrite this as v2 is equal to specific volume at 2 over A2 multiplied by 0.2 times A1 V1 over little v1. Does that make sense? I know that, we've tried this now 3 times, but hopefully this is clear how we got this, right? This just comes from this expression, but I subbed in that m dot 2 is 0.2 times m dot 1. Right? And we could do the same thing here, say that v3 is going to be equal to little v3 times a or over a3 times 0.8 times a1 v1 over little v1. Right? And these were the things that I wanted to know, right? I wanted to know these different velocities. So now I have this as a function of stuff that hopefully I know, right? So A1 V1 is given to me, right? The area at 2 I found. The area at 3 I found. Again, A1 V1 is given to me, right? So the only things that I don't know here are these specific volumes. So if I can find the specific volume at state 1 and the specific volume at state 3, then I can get answers here. Right? So what I would like to do at this point, right? So it looks like I didn't in here show you how to do that, but I've got the tables down here at the bottom, and I know a couple of things about these states. Right? So state 1 we know the temperature and pressure. So state 1 P1 is equal to 10 bar and T1 is equal to 500 degrees Celsius. So here I could look here and I can see, well, 10 bar is going to be 1 megapascal, right? And 500 degrees is on this list, right? So 1 and 500 degrees, I think is this one here. So I'd pull off this specific volume. So I can get specific volume at state 1. At state 2, I know that the pressure is 8 bar and that the temperature is 400 degrees Celsius, right? So 8 bar is 0.8 megapascals and 400 degrees Celsius is right here, right? So this is V2, right? So I have values for V1 and V2. Now the next one's a little trickier, right? So state 3, we know that the quality is equal to 0.9 and the temperature is equal to 90 degrees Celsius. So now I'm going to find my rho for 90 degrees Celsius. Now this one is nice to me because in the textbook tables, it doesn't write it out here as 0.001036. It would write it as V times 1,000, and this would just say 1.036, right? But this version of the table is nice to me because they took the extra space to write down all the zeros. So they probably squished all the other numbers around a little bit. So here, if I want the specific volume at 3, which is a function of the quality at 3, that's going to be equal to VF plus X3 times VG minus VF. Right? So in this case, that's going to be 0.001. 0.036 if you want to write it, but it's probably not going to matter too much, times 0.9 multiplied by 2.36 minus 0.001. And the answer that I got for that one was 2.125 meters cubed per kilogram. Now, this number, I gotta say, does this number make sense? Right? So I'm 90% of the way between this number, which is basically 0, and this number, which is 2.36, right? And I got 2.125, right? So probably that's close, right? It's not outside the range, and it's much closer to the high value than the low value, which is what I expect, right? So now I've gone through and I've found the specific volumes, right? So what I did in the path I took here in the notes was a little bit different, right? So remember, we did construct this equation, which we didn't know anything about, right? So then we got to this equation, right? That if the mass flow rate at state 2 is 20% of the mass flow rate at state 1, then the mass flow rate at state 3 must be 80% of the mass flow rate at state 1, right? That just comes from the sum of all these m dots is equal to 0. So then the next thing that I did, instead of subbing it into that other equation, is I just found the mass flow rates. So here first I worked out, because I knew the volumetric flow rate of the mass at state 1, and I divided by the specific volume. And now this gave me, it was telling me that the volumetric flow rate was meters cubed per minute, but I wanted this to be in seconds. So I got my units right here. So I took kilograms per second or per minute multiplied by 1 minute for every 60 seconds. So I divide this number by 60 and I get 11.1. 20% of that is 2.2. 80% of that is 8.9. Does that make sense? Right, so then I came to here, right, and this is where we were talking, right, where we made these expressions for the velocity, right? So what we did was now we fixed all these states, so we knew these specific volumes, so then I could put these numbers in and get velocities, right? So my velocity at state 2 was 17.1 meters per second, and my velocity at state 3 was 10.7 meters per second, right? And these became meters per second because I divided those mass flow rates by 60, right? If I just left the numbers that they gave me, then I would have ended up with a velocity in meters per minute, right? Which may have been okay depending on what the problem asked me to do, right? Just the numbers would be a lot bigger, right? They'd be 60 times bigger, right? So now, you know, one of the things that we always try to do at the end is say, like, does this make sense, right? So first things first, I can't prove that I'm wrong because of the units. That's the first thing, because I don't always have intuition about what a problem looks like, right? But I can check the units, right? So if I got meters squared per second, then I would know that my answer was wrong, right? Because velocity has to be distance per time. So at least here, the signs make sense. The magnitude, or not the signs, the units make sense. Now, because we set this up, right, as this equation, right, as the mass flow rates in minus the mass flow rates out, we should always get positive mass flow rates, and we should always get positive velocities, right? Because the negative, the fact that this is coming out, is already incorporated in this negative sign, right? I could, if I wanted to, although it could make things trickier, I could just have this equation be dm by dt is equal to the sum of all the mass flow rates. And then I could have the mass flow rates in be positive and the mass flow rates out be negative. That's kind of what you'll end up be doing in fluid mechanics. But we set these up so that we set them all up so that they should be positive quantities. So if you end up getting a velocity that's negative or a mass flow rate that's negative, it means one of two things. It means when you drew your control volume, you mistook something that should have been an inlet for an outlet. That can happen sometimes, particularly as you're designing things that maybe you get some backflow in your system, right? If you ever heard of a check valve? A check valve is like an inline in a pipe, and it's like this spring-loaded thing so that flow can only go one way, right? So the flow goes this way and it opens the valve, right? But if flow tries to come backward, then it closes the valve and it can't go back, right? So if you get negative velocity in like a real situation, it could be that you have backflow. So maybe you want to add a check valve, right? But it could also mean that just you misunderstood the problem and you set up a what should have been an inlet as an outlet, or maybe vice versa. Or it could just mean that you made a mistake with the math, right? Which is certainly something that can happen. Happens to me now and again, right? But these are positive values, which is what we expect, right? So we know that that this makes sense, right? But what about the magnitudes, right? Because I can look at the magnitudes here and say, like, well, how come the mass flow rate here is 2.2 kilograms per second, but the velocity is so much bigger than it is at here? It's almost twice as big, right? And that's kind of, you might look at that and maybe a red flag stands up and you say, like, well, that doesn't necessarily make sense, right? Like, shouldn't the velocity be bigger in the place where lots more mass is coming out? And the answer is maybe, right? There's no such thing as conservation of volume, right? And when we start to talk about, there's also no such thing as conservation of velocity, right? We have conservation of mass. And what happens here, right? So there's a couple of things that happen here. The first is that we have a quality of 0.9 here at state 3, right? So that means that most of this stuff is steam, which probably has a fairly low specific volume, right? Or a fairly low density, a fairly high specific volume, right? But it's not like over here, right? And some of this is water. Some of this is liquid water, right? Which is like 1,000 times more dense than steam, right? So that could be part of the reason why this velocity is lower than this velocity over here, right? The specific volumes are different, right? But also look at the areas, right? The area at state 3 is much bigger, right? More than 10 times bigger, right? Like 30 sometimes bigger, right? So this is a much bigger area too, right? And this is like, you've probably done this, played with your hose in like the backyard, right? And the more you cover the hose, right, the faster the water shoots out, right? And if you uncover the hose, it goes out slower. So here, because this area is bigger at state 3, then, that should slow the velocity down too. So I think really, I can't really tell. I don't have any intuition really about what these velocities should be magnitude-wise, right? But I know the units make sense, and I know that the sign makes sense. And with that, I have, reasonable confidence, right? I don't know what the answer is, but I can't prove that my answer is wrong, right? And I liked my process here because I used conservation of mass. I didn't try to conserve the volume. I didn't try to conserve the velocity. I tried to conserve the mass. And the things that I can check look right. So that's where I'm going to leave it today. I did just want to repeat this announcement from the top here that for this week, and I'll send out an email too, I'm not going to have you submit the problems that are on open systems because it's not related to the test. So I want you to take this weekend and focus on getting ready for the test next week. So we'll push this stuff, these chapter 4, these open system problems, we'll push that stuff to the next week's homework. So does anybody have other questions? All right, I will be around at 2 o'clock today for office hours. So feel free to stop in and ask some questions. It can be about this homework, but it could also be about just getting ready for the test and stuff too. Thanks very much and have a great weekend.
Thank you,
Have a great
Professor.
weekend.
Yeah, no problem.
Thank you, Professor. Have a great weekend.
You too. Bye-bye.